Okay, so we just finished up talking about transportation. We first did erosion, transportation, and now let's talk about, we're going to be talking about deposition. Before that, I know I'm going to do a little quick review or clicker question. And this is something that was talked about in the text, but we haven't talked about it yet here, and so I wanted to bring up these terms, and it's something that we use often when we talk about load. Okay, what is the suspended load or whatever. Each stream has a different what we call capacity or competence, and we'll talk about what the terms of these are. Okay, the blank of a stream refers to the maximum particle size it can carry. So what's the maximum size that this stream can carry? So what's the fastest water that it can carry? Okay, that is what we call its competence. Okay, it's like if somebody is really strong and how competent they are. How much can I actually pick up? Okay, that's how competent that individual is in this sense. Okay, well, stream is the same thing. It's the competence or how big of material. Whereas capacity is how much material I can carry. Okay, so as I go downstream, not how heavy it is or how big it is, but how much can I carry down the stream. The total amount versus the largest size. Okay, so that's the difference between capacity and competence. Capacity is the how much can I move down the stream, whereas competence is how big is the particle that I can move down the stream. Okay, so as you go to some of these other areas, you will then have places that you have deposition, right? So, for example, we have what we call bars, which is a point bar, which is a gravel or sand deposit on the middle or the sides of a stream, and it's usually being deposited because the water or velocity is slowing down. Okay, or we have what we call flood deposits. So, for example, when a stream actually floods, all that the stuff that where it's the fastest is right there in that stream. But when the water goes all the way up here, okay, let me see if I can get a pen here. Let's say it goes all the way up here. Okay, now it's the fastest is still right about here, but as you go away, the velocity slows down. So right here at the edge of the stream, little levees start to form. Okay, we call these natural levees. Okay, and you can see them in this picture up here where you have these levees right here along the edge, because that's where as it flows out of the channel, okay, it will slow down here, so all the stuff slows down and falls off right there at the edge, forming these natural high points right there at the edge of the stream. But then the stuff that comes out here is all the fine-grained stuff. So this stuff will fall out back out here. This is the silts, clays. This is all the stuff the farmers like to farm on, right? Because it has really high nutrients from the organic materials during a flood will come out here and actually fertilize the floodplain with the area that gets flooded. That's what a floodplain is. So these flood deposits will be the finer grain materials, whereas the coarse grain materials will be near the edge of the channel or even at the bottom of the channel. Okay, and as this here gets cut, it will be deposited on this side, so it keeps getting cut on another side, deposited on this side, and what happens is the meander moves over, forming this large line of point bars with cutting into the meander on the other side. We'll talk more about that as we go. So if you want to, there's some links up here that you can look at to actually help you understand this a little bit better. Areas that are going to be deposited, where areas where there's going to be erosion, and you can kind of look at that and kind of investigate those a little bit more. Okay, we just don't have time to do those right now. However, here's some more examples of some places that you can look at. So here's some examples of what we call different kind of landforms. Remember, landforms is the kind of feature that you can see or shape of a feature. Okay, and this is what we call an alluvial fan. Alluvial fan is a fan-shaped deposit or landform that is where alluvium all of a sudden gets deposited because the water velocity slows down. And this is often in areas where you have valleys. We have this nice valley here where all the sediment and the water is coming down, but then when it gets to the bottom, you're now not constricted to that valley. You now have a big open valley, so all of a sudden the velocity slows down. If velocity slows down, then all of a sudden the sediment can fall out. And you'll end up having what we call a fan. Okay, so there's this big fan-like structure at the bottom of this stream. These don't happen as much in the eastern United States because these usually happen more in drier areas, like this is the Death Valley. We have this big alluvial fan. They can happen in the eastern United States, but they're just not as prevalent. And plus we have tons of trees, so it blocks it, so we can't see them. However, these also happen in what we call deltas. So alluvial fans happen above water, where you come outside of a valley forming this big kind of cone-like structure, whereas a delta will all of a sudden flow down, then all of a sudden it goes into another water body, and then so when it goes in that water body, it slows down. When it slows down, sediment drops out and forms a delta. So therefore you form all these distributary channels because the water actually can't carry the sediment anymore, so the sediment falls down into these different channels, and you get all these different distributaries. Okay, so anytime you have a delta, anytime you have a alluvial fan, down in what we call the lowlands area, you have deltas often form, or in areas where you have changes in slope difference. So for example, if you remember this diagram back here, look at it back here, okay, oh, went too far. Here's the tributaries here, but as soon as it went down, steep slope, all of a sudden shallow slope, huge change in velocity. Notice you have some distributary channels for a second, then it goes back to this linear channel. Okay, so we call this a braided stream. And we'll talk more about that in a minute, but just to give you kind of understanding, that's forming distributaries, right? Okay, go back to where we were. Okay, so this is actually a very important slide to understand. It's an important slide to understand because this gives us trends as we go through the system. How does the river change through time, or as we go downstream? Okay, so up in the headwaters, you're going to have lots of tributaries. Okay, down in the lowlands, you have distributaries, and in the middle, we don't have many distributaries or tributaries. You just have this nice meandering or bending stream. That's what we call a meander, is a bending stream. Okay, and so up here you're having a zone, what we call the zone of erosion. Down here, the zone of deposition, and this is the zone of transportation in the middle. Okay. Now also notice that as you go downstream, the slope or the gradient becomes less and less. That should make sense because you're going from high elevation to low elevation, right? Where you're actually slowly getting closer and closer to the ocean or the river or whatever it's actually grading itself to. Okay. So also notice the channel roughness actually goes less and less. Up here you have lots of friction, a lot of rapids, waterfalls, and things like that. Okay, and so a lot of zone of erosion is going to have lots of, the channels are going to be nice and rough, lots of turbulence. Okay, but as you get down, you can have less and less turbulence, have more laminar flow, and therefore you have this changing in the way the river is. Channel size goes up as you go down. That should make sense as well because up here you have lots of small channels. You get more and more tributaries. Therefore, you have more water within the channel. Therefore, the actual channel gets bigger and the channel gets deeper too. So both the channel size, which is the width, and the depth actually increase as you go downstream until you get to the distributaries, and then they get smaller again. Okay, because that's because you slow down so much that you're actually distributing out. Okay, now this is the one that some people have a hard time. Oh, discharge. Let's do discharge first. Discharge is the amount of water that flows past you at any given point. The volume of water going past you at any given point. So we basically, let me get a pen here. We call discharge, which we use with the Q here, equals the area of the stream, the cross-sectional area of the stream, okay, there, as it goes across that area, times the volume that goes past it. Okay, so it's the area times the volume. So how much water goes past you at any given time. Well, hopefully this will make sense, but as you go downstream, you get more and more water, therefore you get more volume. The channel has to get bigger, so you get more volume as well. So you get a lot more and more water as you go downstream, or more and more discharge. More and more discharge as you go downstream. I'm sorry about that. Okay. Now the last one here, which we call flow velocity, is one that's harder for people to understand. Up here in the headwaters, remember we have more friction. And because we have more friction, the water actually slows down. There's a lot more power behind it because you have a lot more you have more gradient, okay, so more gravitational push on it. But because you have so much friction and turbulence, the water is slower. But as you go downstream, there's less friction, because you have bigger channels and therefore not touching the sides as much, therefore it actually speeds up. So the water actually speeds up as it goes downstream a little bit because of the force behind it. So you have more force behind it as you go downstream, or more velocity. Now something else that's actually kind of weird or kind of interesting to figure out. If you look upstream, the stream valley is this nice V shape to it. whereas downstream it has this nice U shape to it. Now that actually is a pattern as well. In that pattern, what's happening here is up here the river wants to cut downward as fast as it possibly can, and therefore it actually will dig down, forming this V shape to it. But down here it's actually getting closer and closer to the sea level, and so instead of all of the power going to digging down, the power now goes side to side. Okay, so as it goes side to side, it's going to actually widen the channel, forming this nice little U shape to it. Okay, now this principle of changing the shape of the river, this is an erosional landform where it's cutting down into the structure. This is an erosional landform too, but it's actually moving side to side instead of up and down here. Okay, so this would be an example of a river in an erosional valley, and this would be an example of a river in a depositional valley, or in a zone of transportation. Okay. So what this principle that we're talking about here is where the river is going to try to dig down in the upland area and then actually start to dig side to side in the lowland area, is a principle that we call base level. Now this idea came about from a guy named John Wesley Powell. He's one of my heroes in a sense, geological heroes, right? Scientists. He actually was, I think I remember, a captain during the Civil War. And he actually blew his arm off. He actually, if you notice in this picture, you can see he has an arm on this side, but on this side there's no. The arm is just the actual picture cuts it off, but he doesn't have an arm on this side. He only has one side because he got it blown off during the Civil War, and they had to amputate it. Okay. Well, what's significant about this guy is he was one of the first directors of the United States Geologic Survey. And he was also one of the first persons to explore the Grand Canyon. It's amazing what he did. He actually went down and floated down the Grand Canyon with some of his men, and went down with only one arm. He was one of the first people to do it. The rapids in that area were just huge. And here's this guy going down and actually climbing cliffs and doing all this stuff with only one arm. So you think you have it bad. This guy did a lot with what he had. But anyways, what he came up with is this idea that a river will only cut downwards, or the lowest elevation in which a stream can erode is coincident with sea level or with some kind of base level. Okay, so for example, this river is going to cut down, but it's not going to cut down below sea level and then go back up. That would defy the laws of gravity. Okay, if it's going to go uphill. What would happen is if it did have elevation was like this, what would happen is it would fill up this with sediment, okay, and it would grade back to this grade here, where the water is the higher elevation here, lower elevation here, as it gradually declines as it goes to the ocean, okay. But so whereas if there was a erosive, if let's say there was sediment here, what the river is going to want to do is cut down through that sediment as much as it can until it gets to that gradient where it goes to sea level. Okay, so I'm going to show you some examples of this. Okay, so here's a stream, and the river right now is in gradient. It is in equilibrium, so it actually is going and slowly grading itself to the ocean. Now let's say we had an earthquake, and that earthquake goes up, causing this bed to all of a sudden go up. Well, the river now is actually higher than what it wants to be. So it wants to erode down into the sediment because it's trying to, the pull of gravity is pushing it down faster, and so it's going to start cutting into the bed. Okay, so this is part where we have a waterfall here. It says it's out of sync or out of equilibrium. It will slowly cut down, and as it cuts down, it's going to slowly get back to its equilibrium again, back to that ultimate base level. Now, the ocean can act as a base level, as the ultimate base level, but other things can act as temporary base levels. Okay, so for example, a lake or another river. So we can grade to that river or grade to that lake. Now, what can change these base levels? Well, you could actually have the uplift of the land surface, like in this fault here. Okay, maybe a drop or a rise in sea level. If the sea level drops down, then the river is going to want to cut back down into that. Whereas the water sea level goes back up, it's going to actually fill it in with sediment. Okay, which is a great example of the coastal plain. That's why we have so much sand all over the coastal plain, because when sea level was high, all that water